Okay, so in this lecture we are going to study the density matrix formalism. So this is a generalization of the concept of a state vector. See, a quantum state is represented by a vector in the Hilbert space. Now, essentially, the idea is that a vector in Hilbert space, a quantum state, I should say, in maximal knowledge is a vector, is represented by a vector. The same thing is a vector in a Hilbert space. And what do I mean by maximal knowledge? So maximal knowledge, as we have already discussed, when we were talking about subjective and objective probabilities, or subjective or objective information, maximal knowledge is when the experimentalist has all the knowledge to carry out the experimentation, to prepare the system. Remember how we argued that the coin toss, compare this with a coin toss, where the ignorance or the knowledge was subjective, in the sense that if I have all the CCTV cameras in the world, still, so my state of knowledge depends upon the missing information. And if I know all the dynamical laws, all the torque on the coin, all the CCTV cameras, there's no subjective ignorance about the coin toss. So a quantum state, so this was subjective knowledge. What we are talking about here is the maximal knowledge. So there was some fundamental randomness associated with quantum operations, even if we have maximal knowledge, as we saw. But here we are talking about the maximal knowledge, and such states of maximal knowledge are represented by state vectors. So this state vector does not have any subjective probabilities like the coin toss. But in many scenarios, even in an experiment or in general, we need to deal with situations where not only you have a quantum state of maximal knowledge, but we also need to combine it with subjective knowledge or subjective probabilities. After all, what are we doing? We are quantum mechanics, and our job is to make sense and predictions as much as possible of the experiments. Now, the experiments can be in a state of maximal knowledge, that means the experimentalist has complete knowledge of how to prepare the system, or there can be some coin tosses in the experiment, who's to say. So, density matrix formalism is a way to combine the subjective probabilities like a coin toss along with the essential information which a quantum state carries. So we'll do it with the help of an example. By the way, as a convention, I'll be representing the eigenstates of the z operator as either this, or I'm going to be representing as the this. So essentially these two should mean the same thing. This is the plus 1 eigenvalue, this is the minus 1 eigenvalue of the z operator. So I am going to use either the plus or the up arrow, or minus or the down arrow interchangeably. So this is my convention. Okay, so let's say you prepare a system in a state of maximal knowledge. You have a Stern-Gerlach setup or something that pops out the state, which is also given in the x basis as this guy. So this was the state on the block sphere over here. Which can be represented as a, so this is the state I'm talking about over here. This can be represented as a superposition of plus x and minus x, or up x and down x over here. And the inner product, let's say, yeah, so the inner product plus x plus z square, what does it tell you? It tells us the probability of finding the state in plus x, or the positive eigenvalue x. Again, I am going to be using plus x, the plus 1 eigenstate of x interchangeably. Okay, so this was, so far I was preparing this as a pure state, and what I call as pure states was essentially these state vectors, which as we've already seen, and they represent states with maximal knowledge. So, which essentially meant that the experimentalist has all the knowledge about the system. And that's how I was representing them by a state vector as all the. And we said that we want to generalize this to combine this notion with some subjective probabilities. Consider this experiment. I have another Stern-Gerlach setup, and where I am, someone is sitting with a coin flip, and with the probability, some probability, it pops out a positive z state. With some probability of a coin toss, it's going to pop out a negative z state. So over here I have a statistical mixture. Notice in this setup, the state I am popping out not only contains state vectors, I also have to make use of the information what is contained in the subjective probabilities P plus C and P minus C. So what happens if you measure the system? Well, you get plus Z with the probability P plus Z and minus Z with the probability P of minus C irrespectively. So now what happens when we calculate the probability of plus X? It gives me, see, P plus Z times I was popping up this thing, so this is going to be plus X, this guy squared, and I'm going to get this guy squared, and this probability is going to be half if we have a fair coin. If we have a fair coin, P plus C to P minus C equals to half. What if we calculate minus X? Is going to be P plus Z similarly. Just the inner product of the minus kit with, and it's still going to be half if again we have a fair coin. So now compare this to a pure state. So this was a calculation involving some subjective probabilities coin toss. Let's say we didn't have a coin toss, what I'm calling as your ordinary Stern-Gerlach setup, and I am popping out let's say a state which is a superposition of, I'll normalize this, square root of 2. So let's say I have a Stern-Gerlach setup and I have no coin toss. I am just popping out the state which is a state vector. So, you know, this is as bona fide a state vector. It's a superposition of two things. It's a normalized state vector plus Z down Z, and I am popping this out. This is a covariant superposition of both the eigenstates of the Z operator. So now when you measure with half the probability, when you measure the Z operator with the half the probability, you are going to get this eigenstate, and with half probability you're going to get the minus Z eigenstate. What happens when you measure the x operator? Well, you're going to get this guy. What does it come out to be? And with, of course, the probability of getting the negative eigenstate of x is nothing but the same inner product. This guy comes out to be 0 and this guy comes out to be 1. In fact, you can very well say this is nothing but the plus x eigenstate only. Okay, so what was the difference? This was a statistical mixture with half, let's say probability was half, it was a fair point. Half times I was getting plus z, half times I was popping out minus z. And when I calculated the probabilities of plus x, this was half. And the probability of minus x was also half. Whereas when I was measuring the z operator, both of them were giving me half and half probability. Over here, I have a covariant superposition, and I'm getting the probability of half when I measure plus z, half when I measure down z or minus z, but when I measure plus x or minus x, I am getting 1 and 0. So the conclusion is that statistical mixtures, by statistical mixtures, when I am combining a coin toss or my subjective probabilities with the quantum state preparation, statistical mixtures behave differently than coherent superpositions. We are going to generalize this concept. How to make sense of this thing, or is there a mathematical formalism to calculate these probabilities when we prepare a quantum state using a coin toss? So we come to the density operator. And the idea is we start by calculating the probability of measurement outcomes for the state coming out of black box. And let's say we are calculating it in any direction, not the x direction, z direction. So essentially, let's say I'm trying to measure the spin coming out of a black box in any arbitrary direction n. So what's going to be my formalism? It's going to be this guy. So that's going to give me, this is the probability of my coin toss was yielding plus C, that's the inner product. This is the probability of getting the result plus eigenvalue of the nth direction. So what does it give me? It gives me, I'm just going to expand it out. Similarly, and that gives me that's another way of writing it. This guy. So I'm just expanding it. This plus is the inner product, and it's going to be inner product over here also, and this I have sandwiched it between two. So these two expressions are exactly equivalent. So notice what do I have over here? This structure, let me call it rho. This is an operator. This structure helps us calculate any outcome probabilities taking into account subjective probabilities. Notice this spin direction was arbitrary. I could have had any n direction here. Ultimately, this form remains the same. And this structure rho, which I am again going to rewrite, rho helps me express any probabilities or any statistical outcomes of the measurement process. Compare this with the coherent state. This was some constants where C1 square was P plus Z, C2 square was P minus C. So notice one thing, that both psi and rho will show same measurement predictions for the Z measurement but not along any other axis. Density operator, so this structure which expresses a quantum state Combining the subjective probabilities of the coin toss is called as a density operator. And generalizing the density operator, in general, it's a convex combination. A lot of probabilities and pure state projectors. So physically this means prepare psi I with the probability pi, psi j with the probability pj, so on and so forth. This is the density operator. Or generalizing our notion of a pure state or a state of maximal knowledge of the system. So now our postulates of quantum mechanics can be expressed as the state of the universe or the quantum system under picture is given by a density matrix. Remember earlier it was state of a quantum system was given by a state vector. Now that we have combined this with the subjective probabilities, we can paraphrase it again that it's given by a density matrix. Density operator, density matrix doesn't matter. It becomes a density matrix when you express it these in a particular basis. So what are the properties of the density operator? Well, it's Hermitian. You can check all these properties. It's nice to prove these properties. It's a positive operator. That means the following. Essentially, this implies it's a positive operator. So the inner product sandwich between these two has to be greater than 0. It's normalized. That means trace of rho is equals to 1. And why? Well, essentially because the probabilities have to be conserved. This is a probability I'm expressing over, so it has to be conserved. For pure states, rho is equals to rho squared. Not surprising. For a single pure state, my density operator is just a projector, and rho would be equals to its square. So these are some of the properties of density operators. Nice to show them yourself. We'll be I have assigned a few homework problems on the density matrix, but it turns out that the entire formalism of quantum mechanics, all the postulates, can be expressed in terms of the density matrix. We are briefly going to see that also. See you in the next class.